This is the second part of class notes on polynomial functions. And in this video we're going to look at the graphs of polynomial functions. And the first thing to think is if, let's say that we're given any polynomial function, y is equal to a to the n, x to the n, plus a to the n, x to the n minus 1, etc. Then there are certain things about this graph that will be true. And one thing that's true is the graph will be continuous. And the second thing is it will be smooth. And let's talk about what continuous and smooth is. Continuous, remember, is simply a function which can be drawn without lifting your pencil up. So here's an example of continuous. As opposed to, remember we talked about three different discontinuities, as opposed to a problem that looks like this. This was called an infinite discontinuity. Another example was a problem that looked like this, you had a hole. Or the third one was a jump discontinuity. So think about, since the function is continuous, let's talk about jump discontinuity. That would look something like this. So if this is a polynomial function, which it is, that means it's continuous, which means it does not look like this, this, or this. So in some sense, the graph looks like this. It's continuous. The second one is not so easy to see, but it's also true, and that is that the graph is smooth. And the easiest way to see that is to contrast two different graphs which look pretty similar. Let's look at a graph that looks like this. It's continuous. Both of these will be continuous, but here it comes to a sharp point, and another one which doesn't come to a sharp point. And this becomes very important in calculus, but for now it's just realize that this is described as a smooth function. It can be very, very steep, but the turn is going to be a smooth turn. It's not going to have a sharp V point, and that's what we mean by smooth. One thing about polynomial functions is they're characterized by very specific in behavior. And what we mean by in behavior is what does the function look like when you get far away from the origin? And in particular, polynomial functions are going to be well described or well defined at the extreme. So they have well defined in behaviors. And let me show you an example. Let's say you had a function which was pretty complicated when you were near the origin, but as you got away from the origin, it went to infinity, positive or negative infinity. In this case, positive infinity. And let me look at another case like that. The way they describe this sometimes is that in the middle, the function may be very complicated, but as you get far away from the origin, it becomes much less complicated. In fact, it follows one of 4 different patterns. Well, it turns out that all polynomial functions have well-defined in behaviors. And what we use something called the leading term test or the leading coefficient test to describe what that in behavior is. So let's talk about that. Let's talk about the leading term test. It's probably more commonly called the leading coefficient test, though your current book uses the term leading term test. Leading term test. And it simply says this. Let the leading term be a to the n, x to the n. If a to the n is positive, and n is even, an even number, then the end behavior looks like x squared. What I mean by that is that the end behavior will look like this and like this, even though I don't necessarily know what happens in between. And if a(n) is negative and n is even, then we know that it's going to look like negative x squared. And I don't know how complicated it'll be in between, but I will know that that's what it looks at the end. And I'm going to actually take this away and show you an example, and then we'll come back and look at what happens when n is odd. So an example, let's describe the end behavior of y is equal to 7x to the fourth minus 3x cubed plus 6x minus 2. And if you notice, the way that you determine end behavior is first you define the leading term. The leading term here is 7x to the n. The leading coefficient is a to the n, and that's going to be positive because 7 is a positive number. And n, the degree, where n is going to be an even number. So what we already know, we're going to talk about when n is odd in a second, but we know it is n is even and a is positive, and the end behavior is going to look like x squared. And what we mean by this is this graph will end up looking like this and like this, even though we don't really know what happens in the middle, right? So this is kind of unknown. But when x gets large enough, positive, and large enough, negative, then we know that this is going to be the end behavior. And there's two easy ways to write this. One is a more informal way, and we simply say as x goes to positive infinity, y goes to, and we fill in that blank, and then we say as x goes to minus infinity, then y goes to something. And we just look at the behavior, like this is x and this is y. As x goes to positive infinity, what happens to y? Y goes to positive infinity. And as x goes to negative infinity, what happens to y? Y goes to positive infinity as well. And we use limit notation in just a second, but that's enough for what we're doing right now. Now let's look at what happens when a is negative. I'm sorry, when a is positive, an is positive, but when n is odd. In that case, the end behavior will be like y is equal to x cubed. So it'll be positive here and increasingly negative there. And I don't know what it looks like in the middle. It may be very complicated in the middle, but that's what it looks like at the ends. If an is negative and n is odd, then it looks like y is equal to minus x cubed. Negative x cubed, of course, is flipped, so it looks like that, and it may be somewhat complicated in the middle. So that's actually something that you're going to memorize right there. Right? That you have 4 different possibilities. And I'm going to just rewrite this so that it's in a little easier way to remember it. You're going to have n even, n odd, an positive, an negative. This one is going to look like this. This one looks like that. This one looks like this. And this one looks like that. Another way to remember this is this one looks like x squared. In the middle it can be anything at all. We don't really know. This one looks a lot like y equals x squared at the ends. This one like negative x squared. This one like x cubed. This one like negative x cubed. In the next video, we'll look at some more examples of how to do this and another way to write it.